If you've been following 3D generative AI, you know the pattern. You drop a single image into a model like Axolotl3D or Trellis, and it outputs a highly detailed mesh. But try feeding it a real-world capture, where the object is partially hidden, you only have a handful of sparse views, or you want to edit just one specific region of the geometry, and those models fall apart. They assume perfect visibility. They assume a single viewpoint. And when reality doesn't cooperate, the output either collapses or hallucinates geometry that directly contradicts your input. Today, we're breaking down Axolotl3D, a unified framework from NVIDIA that treats 3D completion, multi-view reconstruction, occlusion handling, and geometry-aware editing as the same underlying problem. It's not just another image to 3D pipeline. It's a mathematically rigorous, multimodal conditioning system designed to anchor generation in explicit geometric constraints. Let's look at how it actually works under the hood. The fundamental issue with most current 3D diffusion models is that they're optimized for a clean, idealized setting. They take one image, learn a massive 3D prior, and generate a mesh. But in practice, your input is rarely clean. You might have partial point clouds from a depth sensor, visibility masks from segmentation, and camera poses that are slightly noisy. Previous research addressed these challenges in isolation. Some focused on model completion, others on cross-view consistency, and others on latent space editing. But they operated in silos. Axolotl3D's core insight is that these are all manifestations of constrained 3D completion. The model doesn't switch modes. It takes a unified set of conditions: multi-view images, per-view visibility masks, camera parameters, and a partial point cloud. The point cloud acts as a hard geometric anchor. The masks tell the model where not to trust the image data, and the camera parameters lock everything into a shared 3D coordinate system. Everything gets fused into a single diffusion process. Let's get into the architecture, because this is where the engineering really shines. Axolotl3D is built on top of Axolotl3D 2.1, which already has a strong foundation with a shape autoencoder and a flow-based diffusion transformer. But the original backbone only handles single-image cross-attention. Axolotl3D replaces that with a multimodal fusion pipeline. First, visual encoding. Each input image is processed through DNOV2 to extract spatially aligned features. But raw image features don't inherently know where they exist in 3D space. That's where Plücker embeddings come in. For every pixel, the model computes a 6-dimensional ray representation built from the cross product of the camera center and the ray direction, paired with the direction vector itself. This gets average pooled to match the image feature resolution, projected to the correct channel dimension, and added directly to the visual features. Now the model knows exactly which 3D ray corresponds to which image patch. Next, geometry encoding. The partial point cloud is fed into Vec set X, a fixed-length latent set representation portrayed on ShapeNet. This compresses thousands of scattered points into a compact, permutation-equivariant token set that preserves local surface detail without being sensitive to point order. Then comes the fusion. The visual tokens and geometric tokens are processed through modality-specific gated feed-forward networks to align their channel dimensions. Learnable embeddings are added element-wise to differentiate the modalities. Then, everything gets concatenated into a single condition token sequence. The real architectural innovation happens in the cross-attention layers of the diffusion transformer. Instead of standard attention, Axolotl3D uses mask-biased cross-attention. The visibility masks are patchified and converted into an attention bias matrix. Occluded regions receive a hard negative infinity bias, effectively zeroing out their contribution to the attention scores. Unoccluded regions and the point cloud tokens receive a zero bias, allowing them to attend freely. This prevents the model from hallucinating geometry in masked areas and forces it to complete the shape based strictly on the visible evidence and the geometric anchor. A model this flexible needs to be trained on a massive variety of conditioning regimes. Axolotl3D doesn't rely on curated real-world datasets alone. It synthesizes diverse training scenarios on the fly from large-scale 3D mesh datasets like Trellis 500K. During training, every mesh is normalized, surface points are sampled, and 150 virtual cameras are rendered. Then, the model randomly samples one of 4 augmentation strategies with equal probability. First, sparse views with occlusions. It picks a few non-overlapping camera views, applies random brushstroke or bounding box occlusions to the images, and removes corresponding surface points that fall behind those occlusions. It also randomly masks the point cloud to prevent the model from over-relying on geometry alone. Second, large area point dropout. It simulates extreme partial observability by randomly selecting an axis, thresholding points along that axis with a smooth probability gradient, and filtering out cameras that could see the missing region. This forces the model to infer deep structural priors from very sparse cues. Third, editing scenarios. It simulates user-guided shape modification by masking a 3D bounding box on the surface, removing those points, and providing a single edited view as the condition. The model learns to preserve the unedited regions while completing the masked area. Fourth, single-view generation, which acts as a baseline but is still processed through the full pipeline. This synthetic augmentation strategy means the model never sees a clean, unoccluded single-view image during training. It learns to reason across heterogeneous, partial, and occluded inputs natively. When evaluated on benchmarks like Toys4K and OmniObject3D, Axolotl3D consistently hits state-of-the-art metrics across f-score, voxel IOU, and chamfer distance, both with and without synthetic occlusions. But the real test is robustness. When the researchers swap ground truth depth for predicted depth from depth anything v3, performance drops across the board, but Axolotl3D degrades gracefully. It maintains geometric fidelity, because the Plücker embeddings and mask biasing act as strong regularizers against monocular depth noise. They also tested camera perturbation, adding 10-degree rotation noise and 5% focal length jitter, and the model remained stable, outperforming baselines that lack explicit camera conditioning. Ablation studies confirm the architectural choices. Removing the point condition causes the largest performance drop, proving that explicit geometric anchoring is non-negotiable for faithful completion. Removing the mask bias only causes minor structural shifts, showing it primarily acts as a safeguard against occlusion interference rather than a primary detail generator. And replacing Plücker embeddings with simple learnable view embeddings hurts single-view performance significantly, highlighting that explicit camera parameterization is critical when visual cues are sparse. Because the framework is so modular, it plugs directly into existing pipelines. For shape editing, you can input a single view with stable diffusion, mask the edited region, drop the corresponding points from the point cloud, and feed it to Axolotl3D. The output respects the edited geometry, while faithfully reconstructing the surrounding mesh. For single-view generation, they combine it with MapAnything for metric 3D reconstruction, and SAM2 for segmentation. The predicted points and cameras are aligned to a canonical coordinate frame using ground plane estimation and singular value decomposition, then fed into the model to produce complete, watertight meshes. They even demonstrate downstream physics simulation, where the completed geometry replaces fragmented Gaussian splat segments, enabling accurate rigid body dynamics in captured environments. No system is perfect. Axolotl3D is currently trained with fixed camera distances and intrinsics, so it expects the object to be fully visible and properly framed. It also struggles with extremely thin structures, which can sometimes disconnect or get oversmoothed. The model is optimized for geometric fidelity, not texture, so it doesn't predict material properties or albedo. And because it's trained to follow input points faithfully, it's not yet robust to highly noisy or irregular point clouds, like those from structure from motion or Gaussian splats. The authors note that future work will focus on expanding camera diversity, improving thin structure reconstruction, and explicitly training for noisy point distributions. Axolotl3D represents a significant step forward in making 3D generative models actually usable in real-world scenarios. By unifying multi-view reconstruction, occlusion handling, and geometry-aware editing into a single, mathematically grounded framework, it moves us past the era of brittle, single-condition pipelines. The integration of Plücker embeddings, mask-biased cross-attention, and synthetic augmentation strategies shows how careful architectural design and training methodology can solve long-standing problems in 3D AI. If you're working on 3D capture, simulation, or controllable generation, this is a framework worth studying closely. I'll leave a link to the paper and the project page in the description. If you found this deep dive useful, hit subscribe, and let me know in the comments what 3D AI topic you want broken down next. Thanks for watching.